In this tutorial, we're going to look at solving exponential function word problems. And we're going to see two different types of word problems. Some of them are going to be exponential growth, and other ones are going to be exponential decay. We're going to be focusing on solving for the y value in these videos, or we can say it f at x is the value we're solving for. And that would be both at some point in time in the future as well as in the past. So as we go through these examples, you will see that all of the equations that we write will take the general form of this function is equal to a and then b to the exponent x, where a is the initial amount, b is the base, which would describe the growth or decay, and x is the number of growth or decay time periods. Okay, so let's go ahead and get started. We are told a little bit of information about this population of field mice, and we know that they are growing at 12% per week. So that will give us an indication of our growth rate, our base. And per week is important because we're going to be focused on that to ensure that we have the exponent expressed in weeks, okay? Because that has to match up with our growth rate. The other little bit of information, we are told there are 70 mice initially, so that is our A value. Okay, so the first question, which is asking how many mice are going to be present in 3 weeks, well, that's going to be pretty straightforward. We're just going to say there are 70 mice right now. The growth rate is 1.12, and the exponent is 3. There are 3 growth periods in 3 weeks' time. If we plug that into our calculator, we will get 98.34496, which we would just round to 98, and that is telling us how many mice are present in 3 weeks. Okay, pretty straightforward. Well, what about the second one? Well, the second example is asking us the same sort of question. It's some sort of time in the future. The only thing we have to be very careful about is that this is expressed in days. Okay, so when we write our equation, we're going to still have the initial population of 70, the growth rate of 12%, but this is where we have to be careful. 100 days needs to be divided by 7 in order to be expressed as weeks. And when you're entering this into your calculator, you are likely going to want to use brackets around the exponent to make sure that when you raise that base of 1.12 to an exponent, you do the division and you get 100 divided by 7 as your appropriate exponent. If all has gone well and you type that into your calculator, you should get an answer of 353.3561, and that will obviously be rounded to 353 mice approximately. Okay, so the key thing in the second question here was to make sure that your unit of time matches the growth unit of time. Okay, in part C, the only difference is now we're talking about time in the past. So ago. Now, the only thing that you need to just remember is that if I was to just draw a sketch of, let's say, the growth of these mice, well, we have 70 currently, so that would be the y-intercept. So all I want you to think of is that as time increases, so positive time, then that is in the future. If we want to go back into the past, well, all we do is we take negative time. All right? So we aren't changing anything about the initial population, or we aren't changing the shape of the curve. All we're asking is how many mice were present at some point before. So when we write our equation, we are going to just start with the initial 70 mice, same growth rate. But now we just need to make sure that our exponent is negative. Okay, second check. This is expressed in days. Well, our growth rate was expressed per week. So again, we need to be careful. We're going to take that 20 days and divide it by 7 so that it is expressed as weeks. When you put this into your calculator, please make use of brackets to ensure that your exponent is calculated properly. And if you do that, you will find out that 20 days ago there were approximately 50.637 mice, and if we were dealing with whole mice, entire mice, we would round down to 50. If we were told just to go ahead and round to the closest integer value, we could say there were approximately 51 mice in the field 20 days ago. And I'm glad that that value is obviously less than 70, because we had 70 at time 0, and 20 days ago should have an amount less than 70. Well, let's move on to a couple of examples that look at decay. In this question, we're going to be dealing with a word problem that involves exponential decay. And we can identify decay questions because typically they will tell us that a particular population, or in this case the value of a car, is decreasing as time goes on. So in this case, a new vehicle is purchased and they're saying it loses a certain percentage of its value for every year that it's owned. The $32,000, well, that's going to be our initial, or the A value, the initial amount of the vehicle. And then 4 years is going to be the time period. Okay? A little check to make sure. They're asking us about years, and sure enough, 15% of its value each year. So we won't need to convert the 4 years to match the decay rate period. All right. Well, where do we start with these types of questions? Well, the only real piece of work we have to do is we have to actually determine the decay rate. Okay? And how do we get the decay rate? Well, we're going to take 100% and we're going to subtract the amount that it loses, which is 15%, and that gives me 85%. Now, 85% expressed as a decimal is 0.85. So we are going to have a decay rate of 85%, and that will result in the car losing 15% of its value each year. Okay? If we interpreted the question and we just put in 0.15 as our base in our solution, that would be indicating that the car loses 85% of its value every year, and that certainly isn't the case. Okay, so to go ahead and calculate it, the value of the car is going to be equal to, well, we need the initial amount, so that is $32,000. Then we place our decay rate in there, 0.85, and then we need an exponent, which is the number of decay periods. And in this case, it's decaying 15% per year, and we're being asked about 4 years in the future. If we do that, the value of the car will be $16,704.20. Okay? All right, let's look at a special type of decay, which is called half-life. Okay, this question here is a half-life question, and we can see that prominently displayed in the question is the words, or are the words half-life, and we treat this as a decay problem, and the half-life clue is telling you the actual rate of decay is 50%, or 1/2. The other little bit of information we need to make sure that we are aware of is the time period associated with the half-life decay. All right? So what we're going to do when we set up our equation is we're going to say, okay, we're going to have the initial amount, the decay rate is 1/2, and then I need to put whatever time period over 1620 years, because that is how long it takes for the substance to be reduced to half of what it previously was. Okay? So, filling in the blanks, we're asked if Professor Johnson has a 120 gram sample of radium-226. We are starting out with 120 grams, and they're asking how much will remain after 100 years, well, that 100 years value, that is certainly not going to be enough to knock this down to a half-life. So we just put the 100 over the 1620 and then enter it into our calculator, and we get an answer. So the answer should be 114.9738 grams, and if we were asked to round to the nearest gram, we could say approximately 115 grams of material would remain.